Hello and welcome to this short clip having a look at some selected acid-base titration and standard solutions questions. So the first one is a typical titration calculation but in multiple choice format. So we need to put an equation together first of all, and the equation needs to be balanced with the correct formula for the species. So this one isn't balanced and neither is barium nitrate the correct formula. So thinking about barium nitrate, barium is 2 plus and nitrate is 1 minus. So we need 2 nitrates for every barium. Now we've got a balanced equation, we can start to process the information that we're able to work out the moles for. So it gives us enough information for barium hydroxide, so we can work out the moles of barium hydroxide as 1.125 times 10 to the minus 3. Looking at the equation, the mole ratio between barium hydroxide and nitric acid is 1 to 2. So doubling the barium hydroxide moles gives us the nitric acid moles. So therefore the concentration of nitric acid is its moles over the volume, and the volume is your 23.35 centimeters cubed converted to decimeter cubed, which gives us 0.0964, and therefore the answer is D. So this is an application exam question, practice type question. We'll look at another one like it, which is not multiple choice, a little bit later on. So this one is a straightforward recall of a fact. So what is meant by the term is simply making sure you learn what an alkali is as defined at A level. So it releases OH minus ions in aqueous solution, and the important parts of the definition are in red. So like we said, this is simple flashcard work rather than practicing exam questions. So this next question asks you in a similar way what's meant by the term standard solution. So it's a solution of known concentration, and again putting this on a flashcard and making sure you look, cover, write, then check, and then repeat that process until you're happy with the definition is the way to go. So this next one is a bit more applied. So you need to visualize the process being described. So let's take each bit in turn. The student weighs a sample of the solid carbonate in a weighing bottle, and the next thing is that they tip the carbonate into a beaker and weigh the empty weighing bottle. So they can work out the mass of the carbonate by difference. So the thing about weighing by difference is it doesn't quite matter exactly what that difference is, so long as you know at the beginning how much carbonate is being dissolved before you go on to make it up to a total of 250 centimeters cubed. So if there's a little bit left behind in the bottle from tipping it in, it's not a disaster, so long as you know exactly how much was on the weighing balance. Now you know how much has gone into your stock solution that is going to be used as your standard solution. We need to make sure that as we transfer this from the volumetric flask to other receptacles, we rinse every time to make sure all the carbonate solution is being transferred. Finally, they carry out a titration using this standard solution, and the standard solution will go into the burette, and the flask will have what we call the titrant, the material or the substance you're trying to work out the concentration of. So the next student suggests 2 possible sources of error. So we might want to think about what's missing. We mentioned the idea of rinsings earlier on. So each time the student changed containers, did all of the carbonate get transferred? So the first statement is incorrect as the solid is weighed by difference. So it doesn't matter in terms of the final result if there's a little bit left behind, because at the point you do the weighing, that's when you need to start making sure that you keep the carbonate being transferred rather than leaving little bits behind on each of your pieces of glassware. The second statement is actually right, because if a small amount of solution is remaining in the beaker, then what's going to happen is the amount you think is going to be in your titration is a little bit less than what you actually have. So error starts to creep into your calculations. So the improvement needed is that the beaker has to be rinsed and the rinsings transferred to the volumetric flask before it's made up to the mark, so that all the carbonate ends up in the volumetric flask. So the final bit is another titration type calculation, but this time it's more unstructured. It gives you 3 marks and you have to actually calculate the minimum volume of the H2SO4 that the student would need to completely react with the NaOH present. So why not pause this for a moment and have a go at this yourself. So welcome back. I'm assuming you've stopped the video and had a go at it. Let's have a look at the question gives us. So they want us to calculate the minimum volume. So that's an N equals V times C type calculation, isn't it? So it's a data moles equation moles answer type approach like before. So we look for the thing that has the information to give the number of moles. So we don't have the information we need to work out the sulfuric acid, but we do have the information we need to work out the sodium hydroxide. So put that data down, and you can turn that into a number of moles, 3.1 times 10 to the minus 3. So from the equation this time round, it's a 2-to-1 mole ratio between sodium hydroxide and sulfuric acid. So therefore, this time round, we're halving it to make 1.55 times 10 to the minus 3. So therefore, we want the volume. So the volume is N over C. So N is 1.55. C is given to us in the question as 6.25 times 10 to the minus 2. That gives us 0.0248 decimeters cubed. But the question wants it in centimeters cubed, so we have to multiply that by 1,000. So that gives us 24.8. Okay, as always, thanks for listening. Until next time, see you soon.